Hello, this is the sixth in a series of videos talking about reaction dynamics for the module CHE 30,042. And so today what we're going to do is we're going to talk about applying some of the knowledge we had learned in video 5. Okay, so last time we talked about essentially deriving and introducing transition state theory as a thing. We ended up with the Eyring equation, and what we're going to do today is sort of, basically learn how to assemble that for specific reactions and try to make predictions using that equation. The reading material is basically the same as it was last time. Most of this refers more to transition state theory than it does applying it, but there are some useful bits, particularly in this book, that talk about similar things to what we're going to go through today. Okay. So, as a start, what we need to do is we need to figure out how to assemble the Eyring equation for specific reactions. Okay, and so the way we do that is we essentially will take a reaction, and the first thing we need to do is we need to rewrite it with the transition state in place. So in this case, we've got reactants going to products, and what we do is we put the transition state in the middle, and we have the reactants in equilibrium with the transition state, and then from the transition state is a direct reaction to make the products. Okay, and obviously this equilibrium has an equilibrium constant, and this reaction has a rate constant, and in order to write the Eyring equation, we sort of worked out how those would give us ultimately K2, and we worked out the Eyring equation kind of explains how it does that, right? The next thing we have to do, and this sort of deals with the partition function term that's kind of in the middle of the Eyring equation, is that we need to work out the degrees of freedom in the reactants and in the products of the equilibrium, which is the transition state. Okay, a key point here is that in this case, for that part, the products are the transition state, not the actual products for the reaction. We're talking about the equilibrium when we're talking about that central part of the Eyring equation. And I'll reiterate that in a second when I bring up the Eyring equation. So, we do the degrees of freedom for the reactant. So H is just a single atom, and obviously then it's got 3 degrees of freedom, three translations basically. Okay, so it's got 3 translations, and this is how we can write its partition function. Likewise, BR2 has got 6 degrees of freedom, so it's 3 translations, 2 rotations, because it's a linear molecule, obviously, because it's it's only got 2 things in it. It's got to be linear, and then it's got 1 vibration because those can vibrate. Yeah, so the partition function is going to be this. Okay, and finally we've got our transition state. Now, some people sometimes get a bit confused about what to do for the transition state, but generally speaking, you just plonk the 2 reactants together. So in this case, the transition state is HBr2. Okay, so therefore it's got 3 atoms, and therefore 9 degrees of freedom. 3 of those are going to be translations, 3 are rotations because it's going to be a non-linear. And generally speaking, if you don't know that something's linear, assume it's not. So it's non-linear in this case. And then there are going to be 3 vibrational degrees of freedom too that account for the abilities of those 2 bonds to move. Okay. Of course, as you might be thinking now, or the Eyring equation, in the Eyring equation, we've already removed one of those vibrations for the transition state. So from the top bit, one of those vibrations is already moved and gone out to the front of the Eyring equation because that's the one that leads to products and is already accounted for. So actually, when we write out the partition function for the transition state that goes into the Eyring equation, it's got 1 fewer vibration. Yeah, so that vibration is the one that gives the products. Okay, so just to reiterate, when we're talking about degrees of freedom, we're talking about this bit here where you've got essentially, your partition function for your transition state up here and partition function for reactants down here. And of course, you've got the Avogadro's number here because this is a bimolecular process. Okay, it's a second order reaction. This bit here is the bit that accounts for that 1 vibration that leads to products, isn't it? If you remember back to last time's thing. So the one way of thinking about the degrees of freedom of the transition state is to think that it's actually 3n minus 1, so you get 8 here instead, and then it would be 3, 3, and 2 in that case, wouldn't it? So that's another way of thinking about it, and you can do that if you like. Okay, but anyway, this is the complete Eyring equation for this reaction, and obviously from here what we can do is we can start putting in orders of magnitude, we can start putting in temperature dependencies, and using that we could start making predictions. Okay, and that's what we're going to talk about doing today. The first thing, however, I want to do is I just want to give you a practice of actually doing that. and I'm going to go through this written on the slide. Okay, so we've got a practical exam question here. It says for the following unimolecular reaction, you've got to figure out the number of degrees of freedom and figure out the writing out the partition functions for it, and then we've got to write out an Eyring equation on the basis of that, and we've got to simplify it down. Okay, so that's pretty straightforward to do, and I'm going to talk you through how to do that on the next slide. Okay, so the first thing we have to do is we have to identify the transition state equation for a unimolecular reaction. Okay, and these are in the equation sheet, but equally I'll have them all in these slides anyway, so you can go back and look for them. So here we've got K1, and that should be a small k, and that is equal to kappa KBT over H, and then you've got this. So this is our changed version of the partition function for the transition state over partition function for the reactant, which in this case is CH2 NH2, isn't it? So let's just put that in, and that's then EXP minus EO over RT. Yeah. Okay, so one thing to note is there's no Avogadro's number here, and that's because effectively both of these will be divided by L, and those will cancel, right? Okay, so now we need to think about our reactants. So our reactant is equal to CH2N2, so that's 5 atoms, and therefore we've got 15 degrees of freedom, and they can be given as three translations. It's a non-linear molecule. Okay, so we've got 3 rotations, and we've got the remainder are going to be vibrations. So that's 9, isn't it? Okay, so that will be that part of it. The products, or the transition state, that is going to be effective. It's exactly the same thing. It's just an activated version of it. So we can just kind of put a star here, or a transition state. Again, it's got 5 atoms. Again, it's got 15 degrees of freedom. Or we can say it's got 14 degrees of freedom if we use that sort of 3n minus 1 thing. So when we write out the equation, we need to take that into account. So the equation that's going to go into the Eyring equation is this: Q3, QR3, QV8. Okay, and that's because we've got one of those vibrations is leading to the products and is already taken into account. Okay, so therefore we can put our Eyring equation together, and basically we just put these things into this part here. So K1 is equal to kappa. We can just say kappa is equal to 1, so we could even get rid of it, but let's just keep it in for now. KBT over H, and then we've got, all of this stuff basically. So it's QT3, QR3, QV8, and down the bottom here it's QT3, QR3, and QV9, and then that's exponential minus E naught over RT. Yep. Again, okay, so this looks the same as above. Just, it's always worth double checking these things, because sometimes you'll forget something, but it doesn't look like I have done there. And so that's our equation, but what we haven't done is we've not sort of, made it simpler. Now, to make it simpler, what we can do is we can use those orders of magnitude. Now, if we think that those orders of magnitude are valid, then we can basically say, well, if they're valid, then we can essentially cancel these two because they're the same order of magnitude, both 10 to the 33 per meter cubed. These are both about 100, so we can cancel those. And, this is 1 over 1, isn't it? So we can pretty much cancel those as well. So we can end up with, essentially, we can say this is equal to 1, and this is equal to 1. And so therefore we end up with, and I'll do this in red again. Actually, I'll do it in blue for the fun of it. K1 is equal to kappa KBT over H EXP minus EO over RT. Now, another way of writing it would also be K1 is equal to kappa KBT over H 1 over QV EXP minus E naught over RT. And honestly, both of these are valid because this obviously calls out the fact that our reactants have got one more vibration than the transition state. So, this is valid, but obviously this part here is going to be equal to 1. So you can basically get rid of it. I don't mind you doing that. That's fine. Okay, now we better remember this one because we're going to come back to this later in this screencast. Okay, but that's basically what I'd want you to do as a beginning. Now, of course, what we can do now with this answer is we can say, right, first and foremost, we know that K1's temperature dependence is just K1 is proportional to T exp minus 1 over T. Yeah, and equally, we know what the values of these are at a certain temperature, so we can work out what the value of A is going to be, because these are all constants. I mean, this is 1, this is, 10 to the minus 23, 10 to the minus 33, I think. And then this is, whatever it is. So for a given temperature, we can work out what that pre-exponential factor is. And again, we'll get back to that later on, but these are the sorts of things I will get you to do. Once you've got this equation, I will then get you to tell me what the order of magnitude of this pre-exponential factor is, and also what the temperature dependence of K or the temperature dependence of the pre-exponential factor are. Okay, so moving on from that, we can now start to ask questions about, how do these compare with other theories, and eventually what we're going to do is we're going to try and compare these to experiment too. So the first thing we're going to do is we're going to try and compare transition state theory to collision theory, okay? And so in order to do that, what we need to do is we need to basically, I'm just going to get the pointer up actually, just bear with me for a second. What we need to do is we need to think about how we can form the transits of the Eyring equation, but where we are taking into account the assumptions of collision theory, okay? And the key point there is that collision theory assumes particles are, hard spheres and they have no structure, okay? So essentially, a collision theory assumes they're just atoms, essentially. It's two structureless hard spheres. It doesn't take into account internal energy, okay? So, we can basically see this as one atom hitting another atom to create a transition state that then yields the products, okay? Now, because these are both atoms, because they're both structureless spheres, collision theory assumes that all they can do is move. It doesn't care about rotations or vibrations. So, again, we're applying transition state theory here in a collision theory sense. Okay, so, both of these have 3n equals 3, and both of their partition functions can be written out as just literally the translation. Okay, obviously the transition state then has 6 degrees of freedom because there are 2 atoms. And then these 6 would be 3 translational, 2 rotational, and 1 vibrational. But of course, this vibrational one's the one that leads to the products, so that's not taken into account in that top part of the equation. Okay, so we can assemble the Eyring equation like this, and this is the result here. So we've got basically, again, we've got Avogadro's number back now because you've got 2 things colliding, so it's a second order process. And all I've done is I've just put these things in here. So there's 3 translations, 2 rotations because it's a linear molecule, and at the bottom there's 3 translations for A and 3 translations for B. Okay, now of course, if we just go back to what we were doing in, a couple of slides back in that example, we could now basically just cancel these out, and say they've all got the same orders of magnitude and work out what this number is. But we're not going to do that. What we're actually going to try to do is use the equations from the table that I provided you in the previous screencast and actually see if we can generate the same mathematical expression for the pre-exponential factor as we can for for collision theory. Okay, so let's just do that. Okay, so things to remember are these are the things. Incidentally, as a complete aside, I will not be getting you to do this in a exam or indeed in an open book assessment. I just want to show you that this is possible to do, and that you should be within your capabilities, but it is a bit tricky in terms of rearranging equations. It's quite long, basically. But these are the 2 equations we're going to use, and we're going to put these in the place of the terms that we showed in a minute ago. So, we put them in, and this is what it looks like. We need to be a bit careful with the masses because obviously the mass of the transition state is the mass of A plus the mass of B. And, likewise, the moment of inertia, you need to take into account the reduced mass of, of the things rather than just using a mass itself. But you know, apart from that, this is pretty straightforward. So this is equal to this, and you know, it's worth sort of remembering this. This part here is actually going to be quite useful, isn't it? Because this looks an awful lot like, you know, part of the collision cross section already. Okay, but anyway, this is what this looks like. Looks a bit horrendous, but fortunately it simplifies quite nicely. And I'm not going to go through the simplification here because it's long and I don't need you to know it, but I will. I've not put it up yet, but I will put up an extra handout on which this simplification is provided. Okay, so you can give it a go if you are so inclined. I know some of you quite like seeing the maths come out. I would suggest that you have the skills to be able to do it. It just requires a bit of time. But you know, like I say, I'll put a handout out that's got it on it. I just haven't done that yet. But let's have a look at this. This simplifies to this. Now, this term here, and we'll compare these in a minute, you know, directly. But this term here is very similar, or it's exactly the same actually, as that term we got for the velocity. Okay. This term, you know, we've still got L there. Kappa is 1, so we don't need to worry about kappa too much. And this term here looks an awful lot like the collision cross section, doesn't it? Yeah. Okay, so you know, already we're seeing that they look pretty similar. And let's actually compare them next to each other. This is the collision theory result, and this is the result without that E factor, that Euler's number at the front. You know, essentially what we're assuming here is that E0 and EA are the same. But you know, if they are assumed to be the same, then these two equations are exactly the same, again assuming that kappa is equal to 1. Okay, so you know what that's telling us is that if we have molecules with no structure, i.e. if we assume that we have hard spheres, then both theories will give us the same result, or pretty much the same result, assuming that these energies are the same. Okay, and it will certainly give us the same result for the pre-exponential factor. Yeah. Okay, so moving on, we need to ask the question, can we use transition state theory to make any meaningful predictions? Okay, and so here we're talking about predictions, say, for example, about the pre-exponential factor in particular, but also temperature dependence. Okay, so if we go back to the general unimolecular reaction like this, we actually did the practical question about 3 minutes ago, where we used some specific species, but you know, regardless of whether it's a specific species or it's a general species, you're going to end up with the same Eyring equation, which is the one I've shown down here, and in this case I've included that vibrational partition function for the products, for the reactant, sorry, in the Eyring equation like this, but this was the result we got, wasn't it? Yeah. So what can we do with that? Well, there's two things we can do with that. First and foremost, we can say, you know, this is equal to 1, and then we know what the values of KB and H, and we know what the value of T is at about 300K. Yeah, we get a value, if we put all those into an equation, we get a value that's roughly 10 to the 13. Okay. And so, you know, K1 is therefore proportional to 10 to the 13 times by, you know, the exponential of minus E0 over RT. Okay, so the point being is the pre-exponential factor is roughly 10 to the 13 per second. Okay, at 300K. The other thing we can do is we can say, what's the temperature dependence? Well, the temperature dependence of K1 is T, EXP, you know, this bit. Okay. And as I said already, these are the sorts of things I need you to be able to do, and these are the sorts of things you need to learn how to do for this course. Interestingly, that prediction of the pre-exponential factor of being about 10 to the 13 bears out. It's not too far off, and in fact, many unimolecular reactions, particularly ones that are quite simple, so you know, either very simple species or they involve simple processes like these kind of isomerisms. Cis-trans isomerism here, for example, you know, these things, they're very close to those numbers. So actually, in that case, what it's saying is that transition state theory is giving us a, you know, despite all of the approximations we've made, and we've made quite a few approximations there, it's given us an answer that's not too far off. Of course, that's not the case for more complicated reactions, and many reactions are very, very far out from that. So, you know, this basic way of doing things might be a bit limited, is what I'm saying there. Okay, question 3. Can we do predictions for a specific reaction? The previous example was a reaction type. Now what I want to look at is whether we can actually get a correct answer for any specific reaction, you know, if we take into account, you know, as much as we can at the moment. And, you know, I've got a couple of questions here. And these are things for you to be thinking about, when you're going through these generally when you're going through the lectures. I mean, what would you expect? Do you expect these theories to be perfect? What do you think is going to limit the accuracy of these predictions? Okay, and I will talk about this in a bit, but it's worth having that thought in your head. So, let's think about this reaction here, this species basically splitting up into these two, okay? And once again, we can go through the same process. We've got two reactants, they're the same, okay? So you've got 3 atoms in each of them. So you're going to have 3 translations, 3 rotations, and 3 vibrations. So that's what we've got down here. And the way I've written it is sort of I've compressed it and put 6 of the vibrations all in here, but it would be better probably to write it out as QV3 here and then QV3 here, but for the transition state, we've now got 6 atoms because those two things have come together, and so therefore 18 degrees of freedom. And that is going to end up being 3, 3, and 11 plus 1. And I've explicitly said 11 plus 1 this time. So another way of doing it, essentially what we're saying is we've got 11 vibrations plus the 1 that leads us to the products. So in the Eyring equation, we just have that 11. Okay, so that's where it is there. Okay, again, it's still got 2 species in it. It's still a biomolecular reaction, so it's K2, and therefore it still has our Avogadro's number in it. Okay, so let's do that. And what we need to do is we need to say, well, okay, one thing we can do. Yeah, we've already said that these partition functions have orders of magnitude. And in doing that, we've effectively said that they have the same orders of magnitude, haven't we? Because we've said, well, QT at 3 is equal to 10 to the 33. So, we've essentially said that whether it's in a, reactant or a different reactant or a transition state, it's always going to be 10 to the 33. So that means we can cancel it. Yeah. And so that's the first thing we do. And it's just the same as we did for the exam question that I went through very briefly. And that's in order to, by doing that cancellation, we can end up with this equation here. So, we cancel one of these, cancel one of these. So you end up with these 2 on the bottom, and you've got basically effectively 5 vibrations on the top. Okay. And so that's what it is. Of course, we could then, one thing we could then do is we could say, well, this is 10 to the 33, this is 100, and this is 1. And then we can get out, an order of magnitude here. But that's not actually what we're going to go do this time. What we can do at this point, though, is we can estimate a temperature dependence. Okay, so as with before, this one's proportional to t to the 3 over 2. This one's proportional to t to the 3 over 2. This is equal to 1, and there's a t here. Don't ever forget about that t. And if you sort of follow that through, 3 over 2 plus 3 over 2 is basically 6 over 2. So you've got t to the 3 at the bottom here. And then there's t on the top, so that's t to the minus 2 when it's all simplified. Yeah, so that's what that does. And don't forget that these dependencies come from the equation. So, you don't need to memorize the equations, but you do need to know the dependencies. And obviously you can look them up for the OBA. And so this would be the temperature dependence. But what we want to do now is we want to basically say, how useful is this simplified reaction, is this simplified version of the Eyring equation for actually making a prediction, okay? And, again, have a think about whether this is going to be good or not. So the way we can do that, we can say, well, this is the equation as if we have structured species. This is the one that TST is transition state theory is predicting, yeah, if we do our simplifications. And what we're going to say is, well, okay, well, maybe this one's the actual experiment, yeah? What we can do is we can compare that with collision theory, couldn't we? And if we compared the two with collision theory and just did K2 structured over the collision theory version, then it would be the same as the process we've already done for collision theory, where we use that to sort of generate that shape, that steric factor P. Yeah, so that's what I'm going to show you now. So we do a prediction for K2, which we did before on the a couple of slides back. Got this equation here, and basically what we can do is we can divide one by the other, and when we do that, this part is the only thing that's different, everything else cancels, and then we cancel what we can and we end up with this. Okay, so we can say this structured divided by that, the ratio of the two is going to give us our steric factor, as it were, and that steric factor is equal to about 10 to the minus 3. Yeah, and this is because of these orders of magnitude here. Now, is this any good? No, it's not. Well, it's not terrible, but it's nearly 2 orders of magnitude, well, it's more than 2 orders of magnitude out, isn't it? So actually, in this case, collision theory is doing quite a decent job. It does a better prediction job than the simplified version of transition state theory in this case, which is kind of funny if you think about how basic collision theory is. The reason that transition state theory falls down here is basically because we've been making assumptions that are totally invalid. Okay, so totally invalid to make the assumption that the partition functions in the transition state and the partition functions in the reactants are going to be the same. Transition state's an energized state. It's very likely to have a very different partition function, and of course it's very, very short-lived, so we can't really measure it. Yeah, so this is our issue, and this is going to be our issue whenever we try to use transition state theory. But it's a fun exercise. Can we do any better? Well, we can do a little bit better. What we could do is we could try to use values for our partition functions for our reactants, which we can of course measure using spectroscopy. We can even perhaps predefine them using our those more advanced experiments that I was talking about in previous lectures. Also, we can kind of either try to measure or get approximate values for our transition state partition function, and if we do that, and this is covered in reaction kinetics page 75, what happens is you get a calculated value for the pre-exponential factor that's about 10 times too small. Okay, so unlike collision theory, which would be 10 times too big, transition state theory is at least going the other way. But it's a bit too small now. Okay, so it's not taking something into account basically. It's the same issue really as collision theory in some respects. There's something that's not being taken into account. So obviously the thing we're missing here is information about the transition state, and that is the thing that's holding us back. So state-of-the-art research that we did talk a little bit about already is using femtosecond laser pulses, and it does give insight into transition states, but really there's no reaction that's fully known apart from the very, very simplest reactions. Okay, and really what you need is transition state theory along with potential energy surfaces and with some tweaks to get closer. Okay, the good thing about transition state theory is this ability to predict temperature dependence, and of course we've covered that today, but also to describe other phenomena such as these two effects that I'll talk about in the next screencast. Okay, so thanks very much for listening. Bye-bye.